Thank you for joining us again as we resume FDP on challenges of autonomous and electric vehicle with session 9 and 10. Your active participation and insight will be crucial in making this session both engaging and impactful. Today, the ninth session will be on topic of second generation of battery for EV and will be delivered by Professor Ashish Kumar Singh. Professor Ashish Kumar Singh is professor at NIT Allahabad, specializing in power system, power quality, e-mobility, and renewable energy integration. He holds a BTech from HBTI Kanpur and MTech in control system from REC Kurukshetra and PhD from IIT Roorkee with over 100 research publications and more than 1100 citations. Professor Singh has made significant contribution to his field. He has guided numerous students and taught courses like electric vehicle technology and power system analysis, shaping the future of electrical engineering. Please welcome Professor Ashish Kumar Singh. Over to you, sir. Thank you. Sir, Ashish sir.
नवदीप जी का डिस्कनेक्ट हो गया था. Am I audible?
Yes, sir. Yes, sir.
Yes, sir.
ठीक है.
So please welcome, sir.
थैंक यू. मुझे आप ये करेंगे जरा सा एक परमिशन कैसे मिलेगी शेयर करने की? हाँ ठीक है.
हो गया सर, आपको अलाउ हो गया.
जी 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 जी. हाँ. So thank you very much, Nikita, for introducing and giving this. I'm thankful to the organizers for giving me this opportunity. Is it visible to all?
Yes, sir. It is visible.
Okay. Okay. I will open the camera after some time. Basically, there is some I have disconnected 2 times. Just because of this reason, I have disconnected the camera. Right? During discussions, we will open it. Right? And if you feel that any immediate attention is required, you can ask in between. So today the topic what I am going to discuss, that is upon the second life battery, or you can also say retired battery. This is a unique sort of problem which the world is actually right now facing, and very shortly we are also going to face after some span of some 8 to 10 years, because it is expected that the batteries which are mostly going to be used in the electric vehicles, they are having a end of life for their first use in electric vehicle. That period is about going to be 8 to 10 years, right? So this is a high time on start thinking of this problem. What will happen about those batteries when they are not going to be useful or they are going to be retired, right? So they are being retired as per the specification requirements that we will also discuss in this lecture. But still they are having some sufficient capacity available with them to be used for some alternative uses, right? And they have identified that this particular type of use, alternate use, where these second life of battery can be utilized, that is related to some integration of these batteries for energy storage purposes in the grid, or some other uses which are going to have some commercial value, rather we shall use the term economical value, and how they can be useful. And in that way, we can use them, we can deploy them for the alternative requirements where they can even contribute after completing their first life. So I will start from this. What is the second life of EV batteries? In general, a lithium-ion battery, when we are talking about the car battery or EV battery, so we will definitely right now the most successful battery for the EV use, that is lithium-ion presently. So most of the discussions, they are focused around this lithium-ion battery. So wherever I'm referring the term battery, so definitely it is lithium-ion battery. I'm not going in detail with the other types of chemistry right now, but definitely the similar type of policy things or similar type of requirements and other things that may also be think of for other chemistries of the battery. So lithium-ion battery is a successful battery because we have some key features of this: high energy density that gives you efficient power storage, then long life cycle, though it gives you extended durability, low self-discharge means retains charge longer, and no memory effect. So this is giving you a consistent performance. So just because of these advantages, the lithium-ion battery is the most usable battery in comparison to other chemistries of the battery. Yet we are still in search of new chemistries which may be useful for more uses of the battery, right? So they are definitely there was some this threshold sort of value was given in a recent IEEE Spectrum article, where they were saying that this weight versus power ratio shall be sufficiently, power versus weight ratio shall be sufficiently low, so that this sorry, I'm just it's reverse. Power versus weight ratio shall be very high, so that these batteries can also be utilized for the purposes where their uses for the critical purposes, such like electrified aeroplane, right? So definitely when we are talking about the vehicle, so electric vehicle is going to be those ships also which are using microgrids within them. We are talking about the drones also, we are talking about the electric aeroplanes also, and definitely the electric vehicles running on the road, they are also a part of it. So when we talk about the cycle life of the battery cycle life decreases with increasing depth of discharge. Depth of discharge is a technical term, we will explain it further. So when these electric vehicle batteries are retired, when they are retired after reaching the end of their useful life in vehicles, that is typically 8 to 10 years, number one. Number two, but they still retain 70% to 80% of their original capacity. And this I was talking about, this capacity, this residual capacity after retirement of the battery, when it is not useful for its primary use for transportation, but it can be used for some other purposes. So if we go about the term of end of life of the battery, so end of the life for the battery was defined earlier as a standard by this USABC, the reference is given below, right? And in their test procedure, they defined it as a 20% drop of cell capacity from the rated value, right? So we are saying it 80%. Number two, a 20% drop from the rated power density for its continuous use at 80% DOD, right? So this depth of discharge is a very crucial term for the battery in terms of battery uses and in terms of batteries usability for the second life. But when we talk about this electric vehicle, this battery goes to this 70 to 80% of the original capacity. But there is a study which about of year 2013. It says that in PHEVs, the battery size is comparatively smaller than the full electric vehicle, right? Because in those cases, the long duration is not required that much, and whenever there is a end of charge in the battery, immediately PHEV comes for the support. That internal combustion engine of that PHEV that comes for the support, right? So everywhere this ICE engine based engine that compensates the battery performance degradation. So even then, when this 80% limit is crossed,
I think some of the faculty members are on the dais, and of the dais online, they all are here. So
this can be suggested as way to extend EV battery life, number one. And it definitely, this particular paper of 2013, it suggests some more research on defining retirement periods of the battery, which are 8 to 10 years right now, with 80% remaining capacity as per the standard given by the US agency, which is being followed globally. But what happens when this period of 8 to 10 years is passed and the battery capacity is also reaches 80%, but PHEV may need not to replace the battery, but what happens? The psychological factors such as range anxiety may cause EV battery replacement after a 20% capacity loss. So here, the more research on the battery retirement period extension or battery life extension, that is overpowered by these psychological factors of the drivers or the owners. So what happens? Instead of immediate disposal, right? And what is the disposal? Disposal is either you discard it, just throw it in the waste, or you recycle it in parts, right? So retired batteries are repurposed, right? So now what we are using, there are two different terms we are using. One is recycle, refurbish, repurpose. We will also take a comparison of these terms. So these batteries are immediately repurposed rather than being immediately disposed of, just for the purposes which are less intensive energy demand. And definitely in comparison to their first life, where they were being used in the vehicle propulsion, but the alternate ways of uses can be found as stationary energy storage, grid balancing, and renewable energy integration, where the intermittency of the renewable energy sources is being compensated with the use of these energy storage systems, right? So this concept of repurposed battery, that is known as second life batteries, right? So here comes the repurpose, means you are going to change it without making a major change in its composition, right? But sometimes some minor changes are required just to make it useful for the uses which they are going to have in its second life. So those refurbishments, etc., are also required. This particular diagram I have taken from a IEEE magazine on industrial electronics, and it clearly defines a comparison between the repurposing versus refurbishing. Here, reference is not mentioned, but definitely I will show the reference in the next slide where it is. I missed here, right? So I acknowledge that it has been taken from that magazine. So this repurposing versus refurbishing for the SLB, means second life battery strategies. Here it is compare as repurposing, that is, here it says that it is battery of the car and this end of life is declared for this first life, right? Then what you do, you select and combine suitable battery packs. There may be battery packs which are not competent for even for the second life. So definitely they will go for the recycle, right? But the packs which are suitable, they are combined, and then they are prepared as a pack for second life product for second stationary application in energy storage in the grid or some other purposes within the this power grid. And they also take part in this applications which comes under the umbrella term of smart grid. So what happens here? Here it says that repurposing is ready to use approach. Reuse native BMS for which it is going to be used. It integrates further elements with system integrators where they are going to be apply it for the new application. Then they are also required to be compatible with the master BMS of the new application. Next, it can be used only in the parallel connections possible because they are not designed for that particular purpose, which is going to for which in second life. Actually, they were designed for the uses in the first life, but that is over. So now they are making compatible. They are made compatible with the second life applications. Clear? So just because of not designed for this purpose, sometimes what happens, this particular battery pack, which is combined with the multiple suitable battery packs, that becomes bulkier rather than if you develop a design product for this, that may be a smaller one in weight or size. Second is this needs the performance verification because these all the packs, they do not come from the similar set of cars. Rather, you may say that these all packs which are going to be used here, they may not have the similar specifications, right? And that's why their performance, they may come from the different electric vehicles which are being used for the different scenarios. Some scenario means there may be one battery pack which may come from a electric vehicle which is being used in the home, right? Rarely used. So it has never gone below the depth of discharge more than 20%, right? But there may be some vehicles which were being used for the commercial purposes. So in those cases, the depth of discharge sometimes goes up to 70%, 80%, right? So definitely the cell life is going to be different for available for the second life because this all depends on the cycle life, right? What is cycle life? We will discuss it later in the next slide, right? Now here comes the refurbishing. What we are talking about the second life, that is about the repurposing only. But how this is different for refurbishing? Refurbishing makes the similar thing is car. It is end of life declared battery, right? But now they open its cells, right? Means different parts are reopened and then they are checked, tested and selected, combine and repair suitable modules in a new battery pack, right? And then comes the refurbished second life product for the stationary applications. So once repackaged, they are basically designed for the new use of battery purposes, or you can say battery energy storage systems, right? And in that case, the battery performance is also guaranteed. But this dismantling, testing, repackaging and certification is needed so that it may be compatible with the newer requirements. It is difficult to what is the know-how of these batteries. It is available for the use after a longer processing time. So in summary, we can say that repurposing, that is faster, that is it's simpler in integration, but battery size is bulkier. In refurbishing, more efforts are done, but ensures reliability and standardization. So now both of these things are available in the market, and this second life battery, which was initially started as a purpose with repurposing of the initial battery in their after their first life, now they are considered for refurbishing also to make a system more efficient and more reliable. Then we were using this term depth of discharge. So let me explain it for you. This is a very technical, it's a simple term, technical term. So DOD indicates the percentage discharged capacity of a battery relative to its total capacity. ठीक है? So हम ये मान लेते हैं कि total capacity initially it was 100%, right? And with this 100 capacity, for an example, we can say this 100 AH battery was there. It was discharged for 20 minutes at 50 ampere. Clear? So 20 minutes is equal to 20 by 60, that is 1 by 3 hours. And if we consider discharge capacity, that goes for 50 by 3 ampere hour. Right? So DOD becomes this 50 by 3 by 100 total capacity into 100 for the percentage purposes. So the depth of discharge becomes 16.67%. Right? For more clarity, we can tell you that if DOD is 100%, means battery is totally discharged. Battery is empty without charge. Right? And if battery is fully charged, means DOD can be considered as 0%. Right? And there is a relationship between DOD increases, state of charge decreases, means you are going in the depth of the battery charge in the for the discharging it, definitely the state of charge is going to be decreased. Now this depth of discharge, lower value or higher value, right? So there is a difference. What is its impact on the battery health? The battery health is related to the battery life. Rather I shall use the word life here, because first life, second life, that is the terminology we are using here. So this higher DOD reduces battery lifespan, right? Means you are discharging for a deeper DOD. It means more time and more current will be required for the charging. So these frequent deep discharges, they cause faster degradation of the battery. So what is the solution? What is the suggestion from the manufacturer? Usually the manufacturers recommend a maximum DOD limit for each battery they design, right? Okay, this battery is going to give you optimal performance for this much percentage of the depth of discharge, not beyond that. So please be careful while using it. Shall not go beyond this particular DOD for a optimal performance. Then comes another term, cycle life. Cycle life dependency is also there. If you are using a shallow or lower depth of discharge, means more charge discharge cycles are going to take place. 20% again charge, then 20% discharge, again charge. So definitely with this shallow DOD, that is going to be a longer life. But deeper DOD, it is going to be fewer cycles and it is going to be a shorter lifespan. I hope I am clear. Similarly, there are some terms or some beliefs or facts you can say about the battery performance with the temperature also, right? So for the higher temperature, rather it is specified as 30 degrees centigrade, causes overheating of the battery, accelerating chemical reactions within the battery, and reducing battery lifespan just because of those temperatures. These additional temperatures, they cause additional losses also in the battery at different points. When a temperature is cold, that is less than 0 degree, rather we shall say, the higher voltages are needed to charge. right? And this is going to put a increased stress on the battery cells. So in this way, this is also going to damage and reducing the battery lifespan. So best practices are keep batteries in a mild range for optimal performance and long life, right? And that is a requirement. Then comes another term I was talking about, that is cycle life, right? And how this cycle life is related with DOD, that is also shown here in this diagram. Cycle life refers to the number of charge-discharge cycles a battery can sustain throughout its useful life before its capacity significantly degrades, right? And this degradation in battery life depends on 2 points. One is depth of discharge, and second is operating conditions, means temperature also is there, or charging, discharging, or depth of discharge is also there, and how this depth of discharge is going to be compensated with the charging phenomena. So if this diagram you see that clear says that if you are using a battery with this 100% DOD from its capacity, clear, so this is going to be the least number of cycles, around 200. If you are using it with 50% DOD, these cycles are going to be around 500. And if you are using with some 30% DOD, these cycles are going to be exceeded more than 1200 cycles, and definitely this is going to give you a longer life. Now next term is state of health. And this particular plot, it clearly indicates what is state of health versus calendar life of the battery in years. So state of health is defined as a percentage of initial energy capacity left in the battery, right? And this plot clearly says that this SOH is decreases with this particular life of the battery in terms of calendar years, right? And what happens, you will find that for the some portion of this plot in number of years, this particular decrement is linear, but after each linear portion there is a non-linear portion also, right? So you cannot say that this decrement in state of health is linear or non-linear. It is a combination of linear and non-linear, and after this 15 years of the life, as per this here, it goes below 80%. Clear? So this clearly says it is going to be useful after this 8 to 10 years of the battery calendar life in use within the electric vehicle, but it is still useful with the useful SOH available for secondary applications, and that's why these are being used as a secondary life. Now question here comes, why we are worried about the secondary life? Clear? Why we are insisting on it? That we will also discuss, but so save this question for the next slides. So this SOH is calculated as a function of both the battery age and impact of temperature. So this is the way of calculation of SOH. There are several methods for SOH calculation or estimation, right? So if you want to go in more details about this SOH estimation, I will refer you a magazine. This particular item of this IEEE Industry Application Magazines of 2024, January, February, this gives you more details about the SOH estimation. In this article, you can find what are the different conventional methods of this estimation or newer methods of estimation, and there are some recent hybrid methods also which are being used for SOH estimation. And what is the this effect of temperature? It clearly says ki from 25 degrees to 30 degrees centigrade means a 5 degrees centigrade temperature rise that reduces a state of health from 80% to 70%. This all are based on the estimation and practical data collected and then estimated, right? And this all is this information I have taken from this workshop report. Year I think I have missed, yes, but I can share it with you. And this is also available with this article of this IEEE transaction on vehicular technology. Then now here comes the question what I was telling you, why this secondary life of battery or second life of battery is important, right? So we were focusing right from the start about the repurposing. Clear? Means we are not going to put more efforts included in the refurbishing. We are directly using it as repurposing with least investment of time and money on it, right? So what are the advantages? Advantages are environmental benefits. Environmental benefits are extending battery life, reduces electronic waste, right? Otherwise they will have to be recycled or earlier. Now in this case you are recycling it at least after some 8 to 10 years again. Means the battery life is, which for the second life they are again going to be totally used for 15 to 20 years. Means 8 to 10 you have used for the battery, and from 8 to 10 to 15 to 20 remaining period you are going to use it for second life, right? So second point here is it lowers the demand, means deferral of manufacturing of the new batteries for the purposes where these second life batteries can be utilized efficiently. What is that? Means deferral of cost investment, means it lowers the demand for the new battery materials, which is definitely rare, and the cost is simply higher just because of these rare earth materials which are the part of the manufacturing process of the newer batteries. Number 3, minimizes the carbon footprint, means it definitely it all is this carbon intensive processes of manufacturing. So if we are deferring the manufacturing, means we are minimizing or saving the carbon footprints which are directly connected with the impact of climate change or the net zero efforts of the government of each country, which are a global binding for all of us. Then comes the economic advantages. Economic advantages of second life batteries are cost effective energy storage solution because they are cheaper in comparison to the newer batteries. And in this way, the utilities, businesses and homeowners, they all are benefited with these lower costs, which are not going to be less efficient for these purposes for a longer period of time. Third, we all know that renewable energy integration is an important aspect for the power system transition. Rather, we can say that this energy is going to be more coming from, we are saying it green energy, right? So green energy is coming from the renewable energy sources, but they are intermittent in nature. So for those renewable energy integrations, we need battery support, and this battery support we get from the SLBs. And in this way, if we combine all these 3 aspects which we have discussed earlier, they become the blocks for the sustainability, right? So in this way, they promote sustainability through circular economy approach. I will discuss a slide on this. So what is circular economy? Circular economy is basically dependent upon the 3R approach. The agenda is reuse, refurbish and recycle, right? Earlier it was manufacture, use, discard as a waste, and again new manufacturing was started. So earlier this was a linear process, right? Now this is a circular process and it is called circular economy or orange economy, where these steps are changed. So again, the similar things are happening in this reuse of existing resources for new purposes, reduced waste, and it minimizes the need for new raw material, means deferral of manufacturing. Here comes a second life battery life cycle in a circular economy. Just a minute. So this particular diagram here, it is available. This clearly says it was the first use of the battery where it was fabricated after the material extraction, right? Material extracted, fabricated or manufactured, and this is the first use of its battery, right? Then after end of first life, this goes to remanufacture, and then it is remanufacture means repurpose or refurbish. Then it goes to second use of second life for energy storage, and after end of this second life, this goes to the recycle, and again this recycle becomes a partial participation, has a partial participation for new material extraction, new material requirements, and it becomes the part of the fabrication of the new batteries for first life. Am I clear? Any questions? Does anyone has any question? Okay. Now, Deepji, am I audible?
Sir, please explain once more this reuse, refurnished, and recycle. Sir, three.
This diagram or earlier diagram, earlier table?
This diagram, sir.
This diagram. Okay. Yes, so what we need that for the battery, we need some raw material, right? So this raw material extraction takes place. Clear? This raw material is used for the fabrication of the new battery here. New battery is being used for first life, for its first life, means battery's first life in electric vehicle. After giving services for 8 to 10 years, end of life is defined as per the US ABC organization, that is given standard of 8 to 10 years life, and 80% of the total capacity is remaining. So it is end of life for the first use, right? So when this condition is met, it may come before 8 to 10 years also, some just because of some manufacturing defect in the battery, but usually it happens only 0.1%. Clear? So when this end of life happens for the first life, it is again going to otherwise earlier cycle this was directly going to recycle, but in this case this is going to remanufacture or repurpose or refurbish. All these three are possible here with you can compare that table which I have shown earlier. So again this battery pack, which is a refurbished pack or repurposed pack, right? It goes for second use of life as battery for storage purposes. It may be at home, it may be at grid level, behind the meter, front the meter purposes, what we study in power system, right? Or it may also be used in some businesses for energy storage. It may also be used as required energy storage for RE integration. So this becomes an energy storage purpose critically, specifically, and use may be simple or critical, whatever that is. But this remanufactures battery, which is now entering in its second life, that is suitable for all these purposes for next 8 to 10 years again, right? Even if you list the applications, I will show you these batteries are some very critical applications, may be used for some applications, and even they may also be used for two-wheelers or three-wheelers, right, in their second life. So now, after completing the second life, now it goes for recycling, and after this recycling, this becomes the part of waste and useful material is segregated, waste goes for disposal, useful materials selected, they again become the part of the remanufacturing process for the new batteries. Am I clear now? सवाल किसने पूछा था भाई?
Sir, yes, it is clear, sir.
ओह, बताना चाहिए था भाई, मैं इंतजार कर रहा था. थैंक यू. अच्छा, अब हम इसी चीज को अगर देखें तो इसका एक टेक्निकल फ्रेमवर्क की बात करें कि हाउ टू गिव दिस फ्रेमवर्क ए ब्लॉक diagram structure, right? And here we are calling it circular economy framework, where this reuse, all these three R's, these three R's, reuse, refurbish and recycle, they are being used. Sorry, ये गया यार. ठीक है, तो अगर हम इस पूरी नया जो सेकेंड लाइफ बैटरी लाइफ साइकिल एंड सर्कुलर इकोनॉमी का फ्रेमवर्क की बात करें तो वी विल स्टार्ट इट फ्रॉम हियर, द बैटरी डिजाइन एंड मैन्युफैक्चरिंग, राइट? And these battery designed and manufactured as a new battery entering into their first life, they go to be, they are being used in electric vehicle, or they are being used in the battery swapping charge discharge stations, right? And then it is going to battery disassembly after this end of life, right? And then it takes place for the visual inspection. After visual inspection, these damaged batteries, right, they go to recycling. But after visual inspection, the batteries which their estimation, SOH estimation is done, what is the state of health of these battery cells, right? And then they are clustered for making it a larger size battery, making it specific for some useful or compatible with some specific application, right? And after this, they are refurbished or repurposed. Clear? As I told you earlier, what is the difference? So when this is repurposed, right? So this purpose product design second life, then it goes to second life battery products manufacturing. Here it was cell, it is now battery pack, and it goes to sales and commercial. Then second life battery applications are being performed, and then after completing that remaining period of 8 to 10 years in second life, it goes for the recycling. Clear? And refurbished, it says that pack dismounting and module testing. Here they give more time and put more efforts. They put more cost on these estimations, and this comes to modules, dismounting and cell testing, right? And they directly send the damaged modules and cells for recycle, but the useful products, they again enter in this product design process, and again they follow this particular route. So in this way, this circular economy model framework of the second life battery can be understood. Clear? So total cycle, you can say it as first life, second life in energy storage, first life in electric vehicle, and finally recycling. The purpose is to minimize the waste and maximize the efficiency. I hope it is more clear now, right? And they are suggesting that for all these processes which are going to happen here, they are going to collect data at every stage, and this data, based on this data and different control algorithms developed after that, they can make a cloud monitoring of the battery, right? And there is also some things which are available in the literature. You can find that they are also trying to give a digital identity to each new battery manufactured. Clear? And they are calling it digital passport of the battery, right? So what will happen means that passport will having all the information of the battery uses. Clear? Means battery uses means what has happened with its first life, means how much DOD it has been processed, means if DOD values are higher during its life, So definitely its value is going to be reduced, its applicability is going to be less. So in this way, those things can be monitored through cloud, through the database, and this physical monitoring, physical efforts or physical labor type of things which are having a major contribution in the cost, right? The refurbishing cost in this process, the manual cost of identification and then this processing required, that goes around 29 to 30%, right? And this 29 to 30% cost is a huge cost for refurbishing. Clear? So if this can be reduced, definitely the cost of the second life battery can be less, and its efficiency can also be monitored through the available data of its uses in the first life. I hope what I wanted to convey, that has been reached to you. And this is about the climate change. The climate change is a major threat. We all know that. So all we are doing, we are targeting that how to face a minimum impact of climate change on us. What are the climate change impacts? We are facing them on daily basis, right? So temperature difference, climate difference, our crops, they are going to be affected by them. So definitely they are to be handled very carefully, right? Then another challenge which is available with all the countries, that is carbon neutrality by the mid-century, that is 2050. So what is carbon neutrality? Carbon neutrality is net zero carbon emissions, means whatever we are generating carbon emissions means whatever we are consuming, that those processes generate some carbon, right? So those processes carbon shall be that particular amount of carbon dioxide generated in my requirement processes shall be that much they can be absorbed by the natural system. Clear? Means this CO2 shall not exist after the consumption of the nature, after the consumption of myself and nature, and it shall be a position of the neutral, means net zero. Generated carbon dioxide is equal to consumed carbon dioxide by the nature, right? So this is a target for the 2050, and that is going to impact that 1.5 degree centigrade change, and that change is very crucial because they are directly related to the with the availability of the water, because if those temperature is going to change, then they say that those glaciers are going to melt and something more disastrous is going to happen. So we shall be very careful with combating climate change, and this is the global shift, right? So in this way, with all these environmental benefits which these SLBs are providing, plus they are being used for the storage purposes with the renewable energy. In this way, these second life of batteries, they are contributing much with for combating with climate change. So these are few trends I am going to share with you, that this global EVs, only cars, right? This I have taken from this IEA website, where you can find the similar data for the two-wheelers also. You can find the similar data for the three-wheelers also, for the buses also. But those numbers were very small, and there was no procedure for getting the cumulative plot for all these. So I have taken this plot only for the global EV. But if you go with this www.iea.org, there you can find the data as I have told you. So this particular plot has an observation for 3 different types of cars. One is BEV, battery electric vehicle. Second is PHEV, that is hybrid electric vehicle, plugged-in hybrid electric vehicles. And third is fuel cell electric vehicle, right? So this fuel cell is having very small numbers. They are at the bottom. PHEVs also are of very small percentage, but the BEVs, they are having the highest numbers here, right? And it clearly says that rapid car adoption is being followed by the users, and by 2030 this number is going to be nearly 40 million electric vehicle globally, right? And that number may increase in next 5 years to 1.5 times. It is going to be increased. That is, in those next 5 years, by 2035 this is going to be 60 million. So definitely the challenges are big, and the problem here is twofold, right? The first is, if what you will do with those batteries which are going to face a end of life after every 8 to 10 years. Clear? So definitely number one. Number two is, if from where you will bring the new batteries required for the RE integration, because I will show the plot about that also, how this RE integration is going to increase. Clear? Because just because of all these things of climate change, zero neutrality, zero carbon neutrality, etc. Carbon neutrality means zero net carbon is going to be these few challenges we are going to have, and just because of these we are adopting EVs, we are adopting RE integration, and we need batteries in support of making these RE integrated power grids more reliable, right? So this is a complete cycle for which SLBs are going to be a big support in that process, with lesser cost and higher efficiency of the system with them. So this accelerating due to government policies and battery advancement and coal reductions. The future of mobility is electric. BEVs will dominate global sales by 2035, because few of the countries, they have declared that they are not going to have this internal combustion engines after 2030 or 2035 or 2040. There are some countries which are going to end the production of these IC engine based by 2030 only. Clear? So here comes a global battery market, energy cost and market share, right? Just a minute. So this particular diagram clearly shows you there are three different diagrams. One is the battery market, right? And it says that the battery market, which is going to increase by almost 10 times in this span of 8 years, right? And this is almost going to be double, almost double, right? Means it is going to be 900 something for doubling, but it is 456. It is almost 1.9 times, you can say, by 2050. So this is the growth in the energy market, this battery market, which is going to be, and these figures are in terms of $1 billion, right? So in this way, this battery market is going to increase, right? And how this is driven? This is driven by growing EV adoption. This is driven by the renewable integration and technologies available for the second life battery adoption or application, right? So just because of this, these particular numbers, they are being fulfilling the requirement of the present scenario. Clear? And we all know that the battery cost is decreasing with the years. Clear? Just because of the change of manufacturing technologies, just because of this cost of available materials reduction. So this levelized cost of energy for the fresh battery, which was in 135 in 2020, now this is 80, right? So this is also less by some 135, 50 is 65. So you can say it has reduced by some 75%, right? Then comes this 70, this is also again more reduction, and this second life battery is also going to be reduced in that purpose, because it is assumed that the second life battery is going to be some 65 to 75% of the fresh battery. So I think it comes in that domain only, in that ratio only, right? And accordingly, this 80 to 53 and this 70 to 45, this cost is also getting reduced. Now, third is percentage share. Percentage share of battery in EV global market, that is being increased by this. It was 13% in 2022. It is 26% it will be 26% in 2030, and it will be 81.5% as projected in 2050. Similarly, for the EV, this renewable energy integration, the market share is also going to increase from 30 in 2022 to 61 in 2031, and then it goes to 88%. That is going to be 88% of battery requirements or battery participation in terms of supporting the renewable energy production. Clear? So this is the percentage. This is the trend basically for the battery market. This is the trend for the levelized cost of energy. The cost of battery, it is reducing, and it comes in terms of the percentage share. So these all terms, they clearly indicate the battery market is going to be very high in number, large in volume, and cost wise. Clear? So definitely the participation of second life batteries, it definitely going to be a useful thing in such scenario of the battery requirement, huge amount of battery requirement, which is presently not possible to manufacture based on the raw material available in this scenario. Now, I am also showing this diagram. This has been just released some 2 days back on this Press Information Bureau website, where you can find that India's renewable energy capacity of 2024 has grown to 209.44 gigawatt, means it is around almost 16% growth it has achieved in comparison to last year, where the solar has achieved a growth of 33.5% in comparison to last year. Wind has achieved around 7.5%. Bioenergy has achieved around 5% growth, and this small hydro has achieved this plus 2.20% growth. Means they are continuously increasing. So it is the target for 2030 for this renewable energy capacity is 500 megawatt as decided by our Honorable Prime Minister. So in this way, it has almost added 28.64 gigawatt in 2024. It has reached to 210 gigawatt almost, and in 1 year. So it is expected that it is on track. It will achieve that 500 gigawatt by 2030. And you know that energy, it is the electricity only, it is the a type of renewable energy which is going to be a useful asset for the growth of the country in terms of economy, in terms of per capita income, in terms of per capita consumption of electricity, and these all are the economic indicators of the economic growth of the country, right? There is a term GDP, and GDP is connected with all these per capita consumption of electricity, per capita manufacturing cost, etc., etc. There are several parameters which become a part of that. So this all is electricity growth of electricity generation, that is in the basis of all this economic growth. And this clearly indicates that this renewable energy capacity addition is required to be supported by the battery storage, right? And definitely the battery which are going to be generated in India after few years, which will enter in the second life battery, they are going to be a big support for in this new scenario of the electricity renewable energy generation. Now this is a plot which is consolidated by the some organizations based on the data available on this government portal of Vahan dashboard, right? So there is organization JMK Research, there is organization Rocky Mountain Institution, and some Niti Aayog participation is also there in developing this diagram, which was developed in 2023. In the beginning of 2023, and it clearly indicates that this is the annual EV sales, clear, and this is the cumulative EV sales. So these numbers are different on the left hand side and right hand side, and in this way this is going to be projected. These are going to be increased as projected by one projection. This dark blue projection is by this JMK estimation, and this the green estimation is by JMK, and this dark blue indication is made by Niti Aayog projections or estimations, right? So it is estimated by this 2030, the cumulative EV sale is going to increase, going to beyond 800 lakh, rather you can say 80 million, I think, right? So this number is going to be a huge number from which the second life batteries are going to come in next few years, right? So these are the different pictures I have shown you about renewable energy integration, renewable energy increase, EV sales increase, and definitely this clearly indicates the cost of battery decreasing. So this is going to be a good picture where these lower cost batteries are going to support our new scenario of the renewable energy generation, and definitely it is going to be a low cost, higher efficiency scenario for the Indian population. So why we know that why we shifted to electric mobility? The electric mobility is very common answers are there, that as a part of broader strategy, we have shifted just to fulfill those requirements of mitigating climate change and those net zero achievements, right? And as we all know that electric mobility reduces carbon emissions, improves air quality, and combat climate change. So these are the basic reasons for the shift towards electrification in the transport sector. Then comes the growing number of retired lithium-ion batteries. If you estimate, this particular paper has estimated this number in China, that it says that retired EV batteries in China, they are going to be historical growth between 12 to 80 times, right? And future projection is it is going to be 1,500,000 ton waste is going to be generated, right? Because it started in 2012 as 0.1,000 ton, goes around 8,000 tons in 2018, and now this number is going to be by 2040. It is projected as more than I think 200 times on the lower estimate, and 200 times, and this is going to be around 400 times on the higher projection side. So this is definitely going to be a big challenge to how to reuse, refurbish, or repurpose these batteries without treating them as a waste, because that waste disposal is definitely going to be a big challenge again. So the growing volume of retired batteries presents a challenge and an opportunity. Challenge is how can these batteries be managed sustainably? Making batteries reuse and recycling is a top priority for sustainability. Opportunity is in what new applications they can be used. That is also being a challenge. Presently, it can be used for some specific applications which are being selected as renewable energy system, energy storage station, using in light commercial buildings, low speed transportation, using in residential buildings, right? These are the specific fields on which hello, any question?
Yes, sir.
हाँ बताइए। अच्छा ठीक है, मैं इसको अगले कुछ मिनट में फिनिश करता हूँ, फिर हम लोग बात करते हैं इसके बारे में, राइट। सो दीज स्पेसिफिक एप्लीकेशंस हैज बीन सेलेक्टेड ऑन द बेसिस ऑफ वेरियस स्टडीज अवेलेबल इन द लिटरेचर. You can find thousands of studies. I was planning to include those studies also in this slide, but that was taking a lot of number of slides more, so I removed that. But you can go through these available literature. You can just search use of second life batteries, SLBs, retired batteries, right? So here you can find multiple literature on which they have studied their uses profitability, right? Is the use of second life batteries in this particular application is profitable or not? So they have found that it is profitable, and these applications which are listed here, they are found most profitable single applications, right? There are different studies which are combining the applications also. If for this much percentage they will be used for one purpose, and for this much percentage of the battery they will be used for second purpose, just to achieve more profitability. And they have also achieved, but they have not found practical in application at single place, so that they have not been considered in this particular diagram. But you can use this paper for your study. That is 2023 December paper. That is on transportation electrification. This is a comprehensive review of second life batteries, right? And it clearly, this particular diagram clearly explains that what is first raw material extraction, second is battery manufacturing, third is first life in EVs, then second life, and then recycling, as I described earlier in different slide. Then comes SLB market, potential and future outlook. That it clearly says that 185 gigawatt hour per year of retired EV capacity is expected by 2025. This is a projection made by Bloomberg New Energy Finance report. References available here. And it is around 75% of the used EV batteries will be reused, and means they will become part in those applications of RE integration rather than being discarded or recycled, right? And there is another study of 2019. It clearly says that SLBs could generate over 200 gigawatt hour capacity by 2030, means this much amount of batteries are going to be available for repurposing, right? And this market value is going to be more than $30 billion, means this is deferral of investment, means if these second life batteries are not going to be used, then we may have to invest this $30 billion for the procurement or manufacturing of the new batteries now, for which they are going to use these second life batteries. So this is the advantage here, and this particular phenomena is called deferral of investment. Clear? Third is economic and environmental benefits. This is reuse battery with residual values rather than recycled or disposed of to optimize their benefits. Then retired lithium-ion batteries may be recycled to recover valuable materials in the last, and discarded if deemed unsuitable for reuse. And definitely there is a certain portion which cannot be reused in a new manufacturing process, so that becomes the waste, right? So if you want to have more idea about this lithium-ion battery recycle, I have found that this article of Nature of 2019 is going to be very informative for you. This is recycling lithium-ion batteries from EVs. Then significant potential of supporting RE generation in India. I have already shown you the numbers. What are the growing numbers of EV use? What are the growing numbers of increased generation of through renewable energy? So definitely, with all these data and with these benefits, the potential for supporting RE generation in India is going to be huge, and we are also going to be part of this journey for using second life batteries. Then projected contribution to India's energy infrastructure that could provide this 1300 to 1870 gigawatt hour of energy storage by 2038. But this particular data is not from the Indian authors. They are just estimation based on some international data available. But this capacity could support 17% to 39% of daily energy generation from renewable energy. And definitely these SLBs are going to support in achieving India's renewable energy targets and reducing carbon emissions. So in this way, we can find them useful for Indian scenario also. Now, what are the challenges for battery reuse? Aging impact is there. Technical and economic feasibility depend on aging performance. As I told you that based on the aging of the battery's first life, that depends on the environment of its use and type of users. Means temperature is also important parameter, DOD is also important parameter, life cycle or calendar life is also an important parameter, how much cycles it has already been discharged in a given calendar year. So in that way, this life of 8 to 10, if more cycles it has completed, it means this calendar year life of 8 to 10 years is going to decrease, right? If it has been discharged for more DODs, this 8 to 10 years is going to be decreased even in the first life, right? So if it is reduced in the first life, definitely the same pattern will appear or reflect in its second life also. So in this way, this is a challenge, how to select a battery directly just by viewing it, it can be used or not. It's still not possible, right? In that way, this SOH estimation, etc., had to be done for the refurbishing, and that's why they say that this particular process is more reliable, right? So just to track this first life aging history or users history, they are giving that this each particular new battery shall be given a digital identification with a digital passport, so that it shall save all the information related to that battery within the battery, right? And you can just plug and play and see the data, how it has been used and how much useful it has remained at this instant of time, right? Then comes the cell inconsistencies, these variations in technical states of cells. Rather, this capacity, internal resistance, and voltages, they basically change. And we all know that internal resistance is going to change. On the higher side, it is going to be more, it is going to generate more heat. So definitely this is not going to be used. Clear? Then there is an aging knee effect that shows a sudden capacity degradation. You can see a plot, you can search it on the Google for understanding, where you find that it suddenly gives you a decrease in the capacity just because of some manufacturing defect or some uneven, uncertain behavior. But it is not that much regular in the battery. It is only just because of some very specific deep discharges or some manufacturing defect. Then comes the key management strategies. They are also challenged for their uses in second life batteries. Risk and benefit assessment, they are very crucial because the safety, right? If the excess heat is going to be generated, then definitely that is more prone to the heating. More prone to the heating means if within a complete new pack of batteries, one particular cell is going to be defective, right? And that is going to be a source of larger internal resistance, larger source of heating, and definitely this is going to create a risk for the complete pack of the refurbished or repurposed battery. Then comes the different policy consideration can be developed, like this digital information scenario, it has been created, or some more policymakers may address the gaps, urgencies, and uncertainties. They are the most important thing, how to manage those uncertainties before starting its second life and after the end of first life. They are to be addressed, right? And this particular study has been performed for the economic analysis. They have considered, this paper was of 2015, right? This is a study made by the National Renewable Energy Lab. It is available in a form of report on the internet, where you can find that this new battery price was 250. So in the second life, they have made this 60% DOD and 50% DOD, right? They have considered two different batteries. One was a pure battery electric vehicle with the 75 mile range, and second was a PHEV which was having a battery support only for 20-mile range with a smaller size of battery because it was having an additional ICE based support. Clear? So in this way, second life application, it was using for this peak shaving of the load curve for a substation, right? And they have found that this BEV75, which is having a larger battery, that has been found more appropriately used here for for their second life use. And the key takeaways are lower DOD results in higher health factor, greater market value, increased salvage value. The refurbished cost is here also, but salvage value is also higher in comparison to other. Higher refurbishment cost, but is still economically viable due to better resale value. Since the battery is in better condition, just because of this lower DOD, more effort is put into optimizing performance before resales. And similarly, these are the negative points with the higher DOD, right? So it is found that BEV75 means pure BEV was having a better value in the second life assessment just because of the larger battery capacity and better longevity in the case of lower depth of discharge values. So this all on the proper battery management that has been explained in this particular paper. Then comes the depth of discharge selection in second life use. So how this 50 and 60 they have considered, this is explained here. We will take it some other time, right? The profitability analysis of SLB integration in stationary applications. So this says that different research papers were available, but I have not included them here for a tabular comparison. But it clearly identified that following the applications which are useful and profitable with second life of batteries. Clear? I have already mentioned them in that diagram, right? And it clearly says when the multi applications I was telling earlier, that is the multi applications, the combination of energy time shift plus peak shaving, such combinations are also profitable, but it is not possible always to have them simultaneously available at one location. Clear? So they are only study there, not for practical purposes they are being employed. It clearly shows that different pricing conditions, application types and combinations, they impact the economic viability of the second life of battery. But these studies, which are in hundreds of numbers available in the research papers, they guide future research in this particular dimension and investment in SLB deployment, and they are also helpful in developing new policies for the SLB deployment. Then SLB price composition, if I say that, it clearly says, as I was telling this 29%, this data I was sharing with you earlier, this 29% is the labor cost, right? Which is basically evaluating the parts of the battery, components of the battery, performance of the battery at the end of its first life. And suppose if this data, what they are trying to explore from here, is available, right, and they can just click it by using some data available on the internet, cloud, or the computer, right? Yes, this is usable, this is not usable. So definitely this particular amount is going to be reduced heavily, right? And so this is going to be more cost-effective second life batteries may be. Clear? And it clearly indicates that this particular paper of 2023, it clearly says that this battery cost, that is almost of 60 to 75% of the between the difference between the first life battery and second life battery. And in that also, the second life battery cost has two different components. One is the second life battery buying cost after the end of first life, and then second life repurposing cost. And this repurposing cost has different components, and out of this 30% is only goes for the labor charges. Clear? And this another 30% that goes for general and administrative. So if that particular data is available only by the viewing, we can control that. Clear? We can reduce that. Then this is the price curve for in the different years available in the same paper. It clearly says that this particular curve for the new lithium-ion battery price, it is reducing, and this is SLB price, second life battery price, that is also getting reduced, right? And this particular diagram on the right side, this scale shows that ESS capacity or battery growth in stationary applications is also visible here. So this shows the applicability and future prospects also for the application of the SLB. Here comes the different, this gives you a comparison of degradation of lithium-ion batteries. They say that different, mainly these 4 degradation mechanisms are available, right? And this clearly shows you that what happens in each degradation mechanism of each type and what are the effects. The effects are increasing internal resistance, lowering efficiency, reducing charge discharge capability, right? So these degradation mechanisms are solid electrolyte interface growth, SEI growth they call, right? And this growth of SEI that blocks lithium flow between the electrodes. Then comes the loss of active material that gives you a lower battery efficiency. What happens in that? Electrode material degrades, reducing active sites for electrochemical reactions, happens in both positive and negative electrode. Then comes the loss of lithium inventory that reduces the energy capacity, decreased amount of lithium available for charge discharge due to SEI growth, electrolyte breakdown, and dead lithium formation. Then last is lithium plating, risk of battery failure. Lithium deposits as metal instead of intercalcating that into the negative electrode, that risks dendrite growth and failure. So these are the main parameters for this degradation mechanism. These are main degradation mechanism. There are more, but mainly literature has these only, right? And this you can find on this a 2022 paper of Energy and elsewhere publication. This is Mohammad Sahajlal, who has written this paper. Clear? A good paper for your understanding, right? Then comes electrode specific degradations. They can say that negative electrode, that is graphite based, impacted by lithium plating, SEI growth, dead lithium formation. Then comes the positive electrode affected by transition metal dissolution, phase changes, and it says positive SEI formation it has, right? And then comes the environmental and operational impact, that high temperature and high currents, they accelerate this SEI growth. SEI is solid electrolyte interface growth, right? And this gives an increasing risk of battery aging and thermal breakdown, basically. Then comes the low temperature and fast charging. This is slow lithium diffusion, increasing lithium plating risk and potassium battery damage. Then this is a case study of SunBat project for of this second life battery for smart grids, right? What they have done at them, they have taken a old marine container, right? And within this container, they have planted this some batteries taken from the old Volkswagen batteries of 4 PHEV batteries, each of 8.8 kilowatt hour. And there they have included this AC-DC converter for efficient power conversion. They are using this battery management for energy utilization and safety monitoring. Then they are using SCADA also for centralized control, right? And energy management system is also integrated for weather forecasting to protect energy needs, grid demand and supply optimization, human-machine interface for user interaction through mobile or computers, right? And they are connected to a solar carport of 8 kilowatt for renewable energy input on the roof of that building, and 3 EV chargers and 1 fast EV charger. They are available with this particular box. Use the local electricity grid. It is also connected with the local electricity grid with the 90 kilowatt peak power capacity it can offer. So economic viability, it clearly says that for SLBs they have used, and these SLBs having the lower cost from euro 40 to 150 per kilowatt hour than the new battery cost of 200 to 300 kilowatt hour, right? And this clearly benefits and clearly calculated that they have some 9% CO2 reduction compared to conventional grid powered buildings. supports clean energy storage for EV fast charging, reduces reliance on fossil fuel based backup power sources. Yes, of course, this CO2 sustainable benefits, they are limited to the availability of the power from the solar. In case it is taken from the grid, so definitely these 9%, these sustainable benefits, they are not going to be those that much prominent, right? So this is a clear model which is in use from last several years. I think it was first report was published in 2015 about this. Yes, it was a workshop report, and now it is a case study from different different papers also, where you can find it. Right, so this is a model. Batteries are available. SCADA is there, EMS is there, HMI is there, DC conversion, DC-AC converters are there, and these are the fast charger and 3 slow chargers. Clear? And this solar panel of the capacity of this 8.6 is also there. Batteries, 4 batteries of 8.6 or something like is also there. Right. So this is a working model of second life battery applications for society, this community purposes they are using, right? So this is all about today's presentation. If you have some question and answers about that, you can ask me here, and if time doesn't permit, you can write me on this by email ashish@mnnit.ac.in. Please do remember that double E is in Ashish, double N in the MNNIT, right? So that is important just to reach me. You can write me on this email, and I hope I will be able to give the answers of your query, right? And if I'm not having the answers ready with me, so definitely I will try to find out, and that will definitely add in my learnings. Thank you very much.
Thank you, sir, for your enlightening lecture. We deeply appreciate the time and effort you have taken to share your valuable knowledge with us today. Thank you once again for making this session so impactful. Now I request to participant, please ask a question, and you can also write in chat box. So there are question in chat box.
There are questions I can see. Which test we can perform on batteries? The basic test is estimation of state of health, right? That is important. Yes, otherwise, there shall be no physical damage on the battery. By viewing, you can see it, right? And the connections, loose connections, or the state of health estimation, that gives you all the parameters which can be directly decide the use of that battery for second life. Can you, good self, send few papers on current important topic? Yes, you can write me on this email. I can share it with you. How green or environment friendly is the refurbishing, remanufacturing processes of the used batteries? Don't these processes leave behind carbon footprint? Yes, of course. Every action of the human that leaves a carbon footprint, but always there is a comparison which particular act is more environment friendly. Definitely the new manufacturing of the batteries that going to bring more carbon footprint in comparison to using these old batteries for these purposes. And they are cost effective, they are effort effective, but they are capable of the research is available. They are capable of giving profitability for energy storage applications, for single use, or this combination of applications also, right? So there are evidences in the literature. There you can find it, read it, right? Which test can we perform? Yes, this is again the SOH estimation I told you. Which standards we follow? Yes, I will have to find it out because in this process of learning in last few days about this second life batteries, I have not found any literature related to the standards. But definitely there must be standards applicable of the new batteries. They might be applicable for this also. I will try to find out and share it with you whenever I will have the opportunity, or you can write it to me, right? So what is the difference between SOC and SOH? Very interesting question. right? You can write it to me. I can share the more details with you, right? So SOH is a long-term health available with the battery, on basis of which we decide its second life application, right? So apart from SOH, is any other battery parameter for evaluating the battery status? Yes, I told you the depth of discharge, which has been used during this process, and basically users pattern is very important for making it useful for the second life, right? So these are the few parameters which we have already discussed, right? Anything else? Good, sir. Can we optimize the charging time of battery by particular charging time like multi-stage constant current charging? Somendra, this particular question is not related to today's talk. Yes, we can talk on this. You can call, you can send me this on my email, and I can reply you. Okay, but not for related with the today's scope. Can battery design effects? Can battery design effects? What does this mean? Okay, you can write me. Achha, this is Jashandeep Singh. Can battery design affects? Jashandeep, what is the question is not clear to me. Design of battery shape. Okay, you are talking about the new battery, right? So my reply will be again for you, not related to the today's lecture, right? We are talking about the available designs, available battery cells, which can be used for further refurbishing or repurposing, right? We can discuss on email regarding this. You can write me. Anyone else? Anyone else having related questions to this today's topic?
Good evening. Good evening, Doctor.
Sirji, namaste.
Namaste, Sirji. So I think question answer you have taken a very informative and very interesting lecture. So congratulations and thanks a lot for sparing your valuable time. At the same time, the statistics which you have given in this lecture, I was also throughout there. So
thank you, sir.
I think this is a very informative, this lecture, and very relevant. Most of the students are working in this area of EV, and especially that second life battery concept and the data that will be. So I think they will be in touch with you. So,
sir, please, I'm also learning for this particular domain. This is basically a new domain.
Very interesting, very interesting, yes, because
it is going
the second life battery and their uses and all. So that is quite new for me also, and I think you have taken a very good topic and sir, very much related to this.
Thank you, sir. Thank you, sir.
Sir, namaskar.
नमस्ते सर.
शैलेंद्र बोल रहा हूँ सर.
अरे वाह. थैंक यू.
कैसे हैं सर?
मैं बढ़िया हूँ. देखो मैंने टाइम से लगता तुम्हारा टाइम मैंने कर ले लिया काफी है.
नहीं सर वो तो.
बट इट्स ए प्लेजर. थैंक यू गोरखपुर टीम फॉर गिविंग मी दिस अपॉर्चुनिटी टू सी डॉक्टर शैलेंद्र कुमार. या
थैंक यू सर. थैंक यू सो मच.
शैलेंद्र जी आप नहाने नहीं आ रहे हैं?
सर प्लान तो है, देखिए.
आ जाइए
जी. सर आने लायक है, आप बता दीजिए. मतलब
सर थोड़ा सा रुक जाइएगा तो मेरे ख्याल से ठीक हो जाएगा. लोग तो आ ही रहे थे, थोड़ा सा रश एकदम से बढ़ गया सर वो मौनी अमावस की वजह से.
थोड़ा डर गए हैं लोग.
नहीं डरे क्या है, वही फर्स्ट लाइफ सेकंड लाइफ वाला खेल है सर. लोगों ने सोचा कि आज टहलने आए 2 दिन रुक और जाते हैं, इस वजह से थोड़ा सा मैनेजमेंट शायद प्रॉपर नहीं रहा. और बट एडमिनिस्ट्रेशन इज डूइंग गुड सर. आइए 2 दिन में ठीक हो जाएगा सब कुछ.
चलिए हम लोग 5 के बाद का सोच रहे
हाँ
हैं।
5 के बाद प्लान कर सकते हैं सर, 5 तक काफी चीजें काबू हो जाएंगी।
मोदी जी का हो जाए पहले उनका तो।
जी जी ठीक है।
PM is visiting on 5th, so we will plan after him.
जी जी सर, जी सर।
We were expecting you in Gorakhpur today, I think. Dr. Twinkle Tripathi is there and there was a activity going on.
हाँ, मैं आपसे बात करता हूँ सर।
उसमें भी आपका रोल है।
जी के लिए मैदान छोड़ देना चाहिए मुझे। मैं आपको टेलीफोन पे बात करता हूँ सर।
चलिए सर।
Thank you, sir, Ashish sir.
थैंक यू नवजीत जी।
Dr. Nodi.
Thank you, Ashish ji.
थैंक यू सर।
Next speaker is also joined with this program. So,
Shall we start, sir?
Nikita, start this program. In a brief introduction will be there.
Okay, sir. Now the 10th session of this FDP will be taken by Professor Sailendra Kumar on the topic of recent technology in EV charging and its classification. Professor Sailendra Kumar is currently working in Department of Electrical Engineering at IIT Bhilai. He has completed his PhD from IIT Delhi. He has worked as PDF at Petroleum Institute of Research Center, Khalifa University. Professor Sailendra research interests include charging station for EVs, power quality, grid integration of renewable energy resources, custom power devices, and microgrid. So please welcome Professor Sailendra Kumar. Over to you, sir.
Thank you so much. Thank you for the nice introduction. And I would like to thank the organizing committee of this FDP, those who have given me opportunity to discuss, one of the emerging areas related to electric vehicles. So not taking much time, I'll share my slides and start discussing few things. In this particular area, I'm working from last 6 to 7 years, I would say. So let's see what are the things on which I'm working and what are the emerging area, what are the classification, how do we classify the chargers of electric vehicles depending on the various parameters. So let me share content only, then put a window, right? So can someone confirm this PPT is visible to all of you?
Yes, sir.
Yeah, thank you so much. Thank you.
Yes, sir.
So, yeah, thank you. So the title of this particular talk, or I would say, this is not a talk kind of thing. This is a general discussion. So, it is required. I'm expecting from the participants to have a very interactive session. Instead of having one-way communication, let's have a two-way communication. A few questions I will ask, then you have to reply. And if you have any question, then immediately you can ask, and then I will reply. And if time permits, then we will also see a simulated model related to the charging of the battery, as well as if suppose any electric vehicles in the rural area, so and there is interruption from the grid side, so how do we charge these batteries under standalone and grid connected conditions. So we will consider one renewable source, and using this renewable source, mainly two sources we will consider. One is renewable and another is grid. So we will see under transition from standalone to grid connected and grid connected to standalone, because see, the battery requires, we can operate this battery in bidirectional, we can control the battery in two ways. It can be charged and just discharged. Everyone knows about this functionality of the battery. So whenever it is required, we can discharge this, and whenever it is required as per the demand, we can charge these batteries. So we can operate these chargers in vehicle to grid and grid to vehicles mode as a well-known technology. But still, In India, the vehicle to grid technology, it is not available. Most of the chargers are grid to vehicle in nature, and they are taking power from the grid only. So we have tried to incorporate this renewables in this particular, lecture, or I would say in our research. And then we tried to solve the problem related to power quality, one of the thing, right? Because if you look into the charger, what is the basic configuration? We have this charger could be multi-stage, right? We may have various stages like AC-DC, then DC-DC, and then the battery, right? So we may have various stages, and these various stages are nothing but these are the power stages, like AC to DC and then DC-DC. So during, if you could find out, we have this AC to DC stage. And the most of the time, in case of AC to DC stage, we have Darby rectifier followed by one capacitor. So simply, as a power electronics engineer, I would ask one question from you people. If I'm putting one Darby rectifier along with the capacitor, what kind of load we are encountering in the power grid, right? Any idea? Anyone who can tell me, right? Let me, if pointer is working. So what a simple question is, I have this power grid, right? Or a simple grid, then one filter inductor is there. And after this, one stage is there. Right, one Darby rectifier I have drawn, and then we have this kind of capacitor at the output of this Darby rectifier. So which type of load is encountered to this supply? This is your AC supply. So can you tell me what kind of load we are encountering over here to the grid? So you will understand the power quality concept from this load only. If you are able to identify the load, types of load, obviously, battery will take some power, or we can connect some resistance over here. So the resistance will draw some power from the utility grid, right? But along with this active power, because resistance will draw only active power. So apart from drawing the active power, it will draw certainly some other components also. So what are those components? Anyone who can tell me? As I told you, I want very interactive session instead of having one-way discussion. So anyone who can unmute and tell me, this kind of information or this kind of reply, what is the load and why we are concerned about the power quality if you have this kind of charger. What is the basic conventional charger? Conventional charger has this bridge rectifier and followed by some DC-DC converter to control the voltage, to control the current which is pumped to the battery. Right? So anyone who's interested to tell this? Anyone from the participants?
This reactive component?
Reactive component.
Resistive load.
Resistor load is there. So some harmonic, active power will be drawn, right? But apart from active power, what are the components which will be drawn from the supply? So somebody says reactive power.
Non-linear load.
Non-linear load, very good. So if we have any kind of power electronics which is involved in the circuit, right? Any power converter, either it is AC-DC, yes, either it is a multi-level, two-level, whatever the converter is there, or uncontrolled converter, it will create the power quality issue, right? So people are considering it as a non-linear load. Now, how we will categorize this nonlinear load? How do we categorize this nonlinear load? Any idea? So nonlinear loads are categorized into two parts, right? One is known as, my tab is not working, otherwise I can write. So this nonlinear load is categorized into two parts, right? Nonlinear load, and I'm writing in short. It is categorized into two parts. One is known as current fed kind of load, right? Current fed, and then voltage fed kind of load. So if you have a Darby rectifier followed by a capacitor, and you want to maintain the constant voltage across this capacitor, so this particular load, it is known as constant voltage type of load, or we can say voltage fed kind of load. Under this condition, if you are considering this circuit, you will realize voltage is perfectly sinusoidal. There is no, distortion, or there is no decrease in the voltage. Why? Because these are the uncontrolled devices, right? So it is not reducing your voltage or the voltage which you have applied to this circuit. If you have applied some kind of thyristor, bridge or controlled rectifier, it can control the voltage across the load, right? So sometimes you can say I'm firing the thyristor alpha equal to 30 degree or alpha equal to 60 degrees, so total voltage will be reduced, right? Average voltage, if you calculate, then that voltage will be reduced. And with respect to reduction of the voltage, you have to draw some kind of reactive power from the source only. But here we are dealing with the uncontrolled rectifier. So uncontrolled rectifier, it is not drawing any kind of reactive component, but make sure it converts this AC into DC. So it will draw some harmonic component from the source, right? Some harmonic component from the source. And how it will draw some harmonic component? So we have some constant voltage at the DC side, and this will conduct for a particular time period, right? So it will have some current which is there for some time. Some of the portion the current is not available, and again it is available. Then for some portion it is not available. Again for some portion of negative half it is available. So this Darby rectifier followed by capacitor is drawing a charger, which is the conventional charger. It is drawing the peaky current, number one, and it is discontinuous in nature. So this is not sinusoidal. And there is one term which is known as total harmonic distortion. If you measure the total harmonic distortion for this particular waveform, the current waveform, the TSD is around 70 to 80%. 70 to 80%. Right? So due to this total harmonic distortion, the total RMS current, right? So suppose we have fundamental current 5 ampere. Total RMS current due to these harmonic component, it will increase to 5.5 or 5.7 ampere. So this 0.5 or 0.7 ampere, it is a harmonic current, I would say. And this harmonic current increase the rating of your transformer, decrease the overall efficiency because heating losses will be there, I square R losses will be there. So as the magnitude of current is increased, there will be a huge I square R losses in the transformer and other components, the protection circuits which you have connected. This will be the power system will become, or the source along with the component will become overrated, right? So that we have to look into it. So due to now this kind of scenario, it is not a single unit, right? It is not this kind of scenario. It is not in single unit. Do you know how many rickshaws currently we are running in the road, right? E-rickshaw. Around 3 to 4 crores e-rickshaw are running on the road. And every e-rickshaw has, so the charger are categorized as an on-board and off-board. And this kind of structure is known as on-board charger. And every on-board charger has Dowd rectifier followed by one DC-DC converter. You can think of if you are putting 3 crores e-rickshaw charger to the grid. So what would be the total RMS current and the harmonics which we are injecting to the grid? So recent technologies, what it is suggesting, first of all, we have to use this control converter instead of having uncontrolled converter. So that one of the issue like power factor corrections. So in case of when we have this power converter based configuration, when load is power factor based power converter based configuration, your power factor is not only P by S. P by S means active power divided by apparent power. Now power factor will become fundamental power factor multiplied by distortion factor, DF, right? So PF will become now PPF, displacement power factor, right? Or fundamental power factor multiply by DF. So your fundamental power factor is always unity, but due to this distortion, due to this harmonic, your distortion factor is around 0.9. So overall power factor, it is decreased to 0.9. And you won't believe, I mean, that's why people are using some kind of PFC converter to mitigate this distortion only when we have these Dowd rectifier in the conventional charger. So this is the issues which we are dealing. So power factor decreases from unity to 0.9, and again you have to provide some kind of algorithm, some kind of converter which can raise the power factor from 0.9 to unity. Right. So this is one of the aspect in which I mean we are dealing, and we are providing some power quality power converter to deal and increase the power factor from 0.9 to unity, and then we can make the input voltage and current sinusoidal. Instead of having discontinuous current, this current will become sinusoidal. Right. So apart from this power quality issues, the motivation and objective for this particular work was like the charging station, the current charging station which we are, developing in our laboratory. This supported with synchronization and seamless mode transitions. Right, we can synchronize with the grid, whatever the battery we have connected. We can synchronize these batteries with the grid using these DC to DC as well as DC to AC stages. And this charger automatically disconnect from the grid under outage of grid. Under outage of grid means in rural areas, still people are not getting 24-hour electricity. Right, only 6 to 7 hour power cut is still there in the rural areas. So whenever the supply is there, it automatically connected with the grid. And if we don't have any kind of power available from the from the grid side, so it can be operated in standalone mode. So your charger will be disconnected from the grid. If you have renewable available, then these batteries will get charged from the renewables. However, if you see the conventional charging station from the production region, these are all grid tied charging stations. And then due to production region, when there is loss of the grid, you have to disconnect or shut down your charging station. You cannot operate it. Right? If you want to operate it, your converter, the DC to AC converter, you have to operate in both the modes. Your converter should support current control mode as well as it should be controlled, and it must be controlled in voltage control mode. However, this multifunctional charging stations is developed to establish supply continuous power to the vehicle as well as to the consumer load. Now, we apart from this resynchronization and connections, we have also integrated this renewable source with the grid. So we can optimize this charging station whenever there is no need for the charging of the battery. Suppose there is no peak hours and no vehicle is available at the charging station. At that moment, the extracted active power can be shared to the emergency loads. Like suppose near the charging station, some data centers or some hospitals are there, which require continuous supply. Therefore, this PV power can be shared with these emergency loads and with the utility grid. Moreover, this charging station can be operated under outage of PV source and utility grid in vehicle to home mode, which turns to increase the utilization factor. So what we have find out, like in case of simple conventional charging station, if utility grid is not there, the utilization factor of your power converter, it is very less. You have to shut down at that moment. You will not get any charging stations, any power to your onboard or off-board chargers, right? Onboard charger could be connected at the point of common coupling as they require AC supply. However, your off-board charger could be connected at the DC side, and these are the high power charging station, or we can say fast charging stations, level 3 charging stations. So the utilization factor in that case will be very poor, right? If you are not operating in a standalone and we are not able to supply the power to these batteries. However, in this charger, even though if some battery is available at the charging station, we can operate in vehicle to home mode under outage of PV, number one, and under outage of grid, right? So if both the sources are not available and batteries SOC is maintained, state of charge, it is maintained to, 80% or 90%, we can say. So this battery can be utilized to feed the power from same power converter to the emergency loads or to the onboard charger. So this kind of functionality we have integrated in the developed charger. The charger is also enabled with the vehicle to grid. Active and reactive power support can be provided. Vehicle to home power transfer, which supporting the local loads in islanded condition, or I would say in standalone conditions. So the grid integration of PV array with electric vehicle battery charging system, it is in demand due to number one, as you can see, there is continuously increase in the fossil fuel prices, and the cost of PV module become cheaper and cheaper day by day. So which has paved way in various way and fast development in the EVs as the future mode of transportations. Other benefits, reduction in the distribution losses. There is bidirectional power flow capability using this charger. So as we discussed, this in the first slide, like it is a conventional charger and it is a unidirectional in nature. However, we are developing a bidirectional charger. It can take the power as well as whenever any source or batteries are there, that power can be utilized to the home, or during peak demand we can support the power grid. So import and export power from the grid to the grid, it is possible. We have used these static transfer switches at the grid site, and these static switches, they improve the reliability of the charger by connecting and disconnecting whenever these grid parameters are not in the limit, right? So there is one standard like IEEE 1547, right? 1547, which defines the standards related to 1547, which defines the connections of your charger with the utility grid, right? So they define some parameter like voltage, magnitude voltage, frequency, and then angle theta. So these three quantities are defined. They have given some range of these quantities, like voltage they have given from 0.8 to 1.1 or 1.2 per unit. For frequency, they have given plus minus not more than 0.2 or 0.3 hertz. And then the angle difference between the output of the converter as well as the angle difference between your grid voltage angle and your converter output voltage, it must be less than 3 degrees. So these three quantities has been defined. If your charger is able to match these three quantities, then you are able to connect this charger with the grid. Otherwise, it will not be allowed to connect with the grid, and you cannot take the power from the utility grid, or you cannot send the power to the utility grid. Another important aspect, we have included this PV feed forward loop. So advantage of this PV feed forward loop is it will tell you what is the magnitude of power which is coming from the PV array, right? So once the grid knows how much power is coming from the PV array, the oscillations in the grid current can be avoided. So this type of feed forward, already the information will be passed to the grid. Now this bulk amount of PV power is coming to the grid because there is reduction in the we can say there is increase in the PV power, or there is a reduction in the number of EVs at the PV powered charging stations. So due to this PV feed forward loop, oscillations in the grid current can be reduced. Certainly there is no increase in the grid current. I mean, it will increase and decrease instead of having various oscillations in various phases under increase in insulations or due to less number of vehicles at the charging station, because the power which you are sending to the vehicles, it will be shared with the grid. So in this case, I mean, it gives you the novel distribution concept of power between the PV array utility and with the grids. I mean, with the these EV batteries. Now, this already we have discussed. So charge is also controlled to operate as active power, achieving various unity power factor, and total harmonic distortion is less than 5%. So let's see few, glimpse of this status and trends of charging stations. So at the end of why this is popular, right? So at the end of 2022, there were 2.7 million public charging station worldwide, more than 900,000 of which were installed in 2022. So about a 55% increase on 2021 stock, and comparable to the pre-pandemic growth rate of 50% between 2015 to 2019. Then within a 1 year, there is huge demand of these electric vehicles, and accordingly, people have developed these charging stations, which around 55%. While most of the charging demands is currently met by home charging, right? So everybody has, suppose, these slow charger, and you can plug in with 16 ampere plug at your home, and within 6 to 7 hours you can charge your vehicle, right? But nowadays the trend is, right, if I have time, right, daytime I'm running my EVs, and nighttime I can come to my home and I can charge it. But you can think about the scenario if EV has a range of 350 kilometers. And you are traveling, your traveling kilometers are 400. So after 350 kilometers, you need to charge your EV to complete your remaining 50 kilometer journey. So what you will do, you have to find out some charging stations where you can charge. You need not to only find the charging station, you have to find some fast charging station which could charge your EV within 15 to 20 minute span of time, right? So home charging is available, but the current need is public charging station, right? Which must be accessible for the common people who can charge their EV within 15 to 20 minutes. So high magnitude of current can be pumped to the batteries. And obviously, I mean, when you are pumping this higher magnitude of current to the battery, your battery must be ready to take that amount of current. So these chemistry and I mean material people continuously working to improve the technologies of the battery, which can take right charger can we can develop the charger which can give you infinite magnitude of current, but the end product is battery. I mean, and the sink is battery, which must be ready to take that amount of 200 or 300 ampere magnitude of ampere current. So, I mean, that battery should support these fast charge. Everybody can say, I can develop the fast charger, no issue. But apart from this fast charger, either your battery is ready to take that amount of current. I mean, if yes, then we can pump that current. If it is not allowed to pump that, because see, battery chemistry and this the material of this health will be deteriorated, and instead of the if the batteries last longer for 5 years, it could be, I mean, we can use in a 3-year or 2-year span time if we are deteriorating the battery chemistry of the battery. So this way, we need to develop these public charging infrastructure which could charge these batteries within a 10 to 15 minute, 20 minute span of time. In dense urban areas, in particular where access to home charging is more limited, public charging infrastructure is key enabler for EV adoption, right? Publicly, I mean, accessible fast charging, especially those located along with the motorways, enable long journeys and all. So the number of fast charging increased by 330,000 globally in 2022. The deployment of fast charging component for lack of access to home chargers in densely populated areas, cities support the goal for rapid EV adoption. So this reference I have taken from this particular website, and you can go through it. I mean, the why this I'm telling you, because if I would say for adoption or growth of EV, it is highly depending on the charging infrastructure, right? So instead of focusing on I would say EV technology, we have to focus on first charging infrastructure. If you are able to provide these charging infrastructure in every street and everywhere, I mean, if you are able to distribute the charging station as a petrol pump, I would say, right? Petrol pump easily you can find out within within less span of time or within your area, and the another is this petrol tank can be filled with 5 minutes or 10 minutes, not more than that. So if this kind of facilities we are able to provide, then these grow, we can think about the growth and technology growth of these EV in EVs. Right. Otherwise, it will be very difficult. Without charging infrastructure, growth of EVs will not be there. So that's why government as well as these private sectors, I mean, those who are big player like Tata, and in India, if you talk about in India, Mahindra, Tata, they are focusing on development of the renewable based charging infrastructure. And they are integrating like with the megawatt of solar plant and then wind plant where the wind is accessible, and then they are developing these highway based charging infrastructure, so that if people are the range of electric vehicles is 350 and another 350 kilometers we have to complete. So within 15 to 20 minutes, we can charge the battery and we can complete our journey. So that kind of scenario we are having. So issues in these sustainable solutions in Indian grid conditions, you cannot ignore the voltage regulation. So there is over voltage, under voltage. Sometimes there is instantaneous voltage change, voltage imbalance. Suppose we are talking about high power charging station or semi chargers. So a semi fast charger. So semi fast charger, we have to integrate this 3-phase supply, and this three-phase supply, sometimes we'll find out the all three phases are not balanced. So some positive, negative, and the zero sequence component will be there, and they are unnecessary, creating heatings and losses in the transformer which you have connected to step down the supply to for your chargers. So we are also providing solution to these over voltage, under voltage distortion, when the instantaneous voltage got changed, when there is unbalance in the voltage. So after we are putting the algorithm, we are filtering these all the components. We are deriving only positive sequence component. These positive sequence components are used further to utilized in our control to control the voltage source converter, which we have utilized in the charger. Then we have cost, reliability, efficiency of grid interface, variability. We have to also sometimes will face the variability of renewable productions. Power quality issues are there. Then we have certainly production issues, short circuit capacity, reverse power flow, lack of some sustained fault current, unintended islanding, which I discussed. Like if you have grid tight system, grid tight charging stations, sometimes unintended islanding may happen and you need to shut down the system. However, the charger which we are developing, that's why I told you, it can operate in when unintended islanding is happening, it can operate it. The charger will be in charger will be in operation. It will not be taken out, from the operation, or you need to shut down this charger. Bidirectional power flow capability is there, and localized voltage stability problem we can also introduce. So power quality issues in the charger, we have various power quality issues like voltage fluctuation, harmonics. Along with fundamental, we may have higher order harmonics like 7th, 11th, 13th, and other. We have DC offset, high frequency wave when we are switching on these power converters at very high frequency like 10 kilowatt, 20 kilohertz, or if you have a SiC or GaN based devices in your charger, then it could increase further. There is increase in the frequency further, which could 40 kilohertz or even 100 kilohertz. So that will create, high frequency wave may create some distortion in the voltage and currents, and that need to be addressed. Then reactive power, voltage regulation, low power factor, neutral current compensation, and load management. So if we categorize this charger, classify this charger, we have home-based charger. So home-based charger is nothing but 230 volt, 15 ampere. However, if you are talking about public charging infrastructure, the public charging infrastructure, it is classified as a AC charger and DC charger. So AC chargers, generally we are talking about semi-fast chargers, and it is rated at normal chargers that is equivalent to your home charger. However, if you are looking into the AC charger, this AC charger, semi-fast charger, it is rated from 7.7 kilowatt to 22 kilowatt, right? DC fast charger is categorized depending on the voltage level, battery voltage. So suppose we have battery voltage of 48 and 72 volt, and the power output around 10 kilowatt, 15 kilowatt with a maximum of 200 ampere, then it will come under the category of level 1 DC charger. The another level which we are having, level 3. So level 3, the output voltage raised from 40 or 78 up to 1000 volt, right? And the power output could be 300 kilowatt to 150 kilowatt. Now, apart from level 2, now people have proposed this level 3 charger, right? Level 3 DC charger. And if I'm not wrong, the power level of this charger, it has been increased from this 150 kilowatt to 350 kilowatt or 400 kilowatt. So you can think about the magnitude of current which we are pumping to the battery, right? 350 kilowatt charger with the 400 or so, magnitude of current we are pumping, so that the charging time could be reduced. So in public charging infrastructure which are installed in the India, we have two types, fast and slow. So we have American based charger, that is known as CCS charger, and the output voltage rating is this. We have one connector gun over here, and it is mostly utilized for four-wheeler. We have Japanese-made charger, that is charge demo, right? And the minimum rating of 50 kilowatt. So it provides the facility for semi-fast charging as well as DC charging. So there is one plug where some pins are dedicated for DC fast charging and some pins are dedicated for these AC charging. And the rated output voltage, it is from 200 to 500. We have one connector gun, and then it could be utilized for four-wheeler. Another type of charger, we have type 2 charger, 22 kilowatt semi-fast charger, 380. The voltage range from 380 to 415. We have one connector gun, and it can be utilized for 4, 3 as well as two-wheelers. However, other side we have Bharat DC, 001. So it is rated at from 10 kilowatt to 15 kilowatt, and it is categorized depending on the voltage level. If you want to charge the battery of 48 volt, then you have to go with this. And along with this 72 230 volt can also be used, these kind of chargers. So one connector gun we have using here, and it could be utilized for 4, 3 as well as two-wheeler. So these are the things. We have some home charging, public charging, then normal and fast AC charging. So these things I have already discussed in this particular classifications. Now, if here we are discussing some work which we have done in our laboratories. So Grid Intec multifunctional smart charging stations we have developed. Now, if we classify these chargers, so these chargers could be classified based on energy source. And some charger could be classified based on the installation, right? Second one could be based on the installation. EV charger can be classified based on the power flow. EV charger could be classified based on the level of charging, based on the cable type, based on the number of supply phases. So if we go to the based on energy source, so it could be classified like if we have solar based renewable is there, then it is very easy to connect these DC chargers. However, if you have grid AC charger, onboard charger could be connected with this. So this can be classified based on the energy source. We have DC sources or AC sources based on the charge installation. So we can say either we are going for onboard charger, slow charger, or off-board charger, which are categorized depending on the level 1, level 2, level 3 fast, ultra fast charger. Based on the power flow, the charger, EV charger are categorized based on the power flow. Either we are talking about the unidirectional power flow, only the power will flow from grid to EV batteries, or we are talking about bidirectional power flow. By the way, by connecting various EV batteries, suppose we have one society, and one society has 300 houses, and these out of 300 houses, suppose 200 houses are having EVs. 200 house owners, they have EVs. So you can think about, because see, the vehicles which, even though your fossil fuel based vehicle, you can think 90% time you are not utilizing it. Only 10% time. Suppose I'm working in some IT companies. I will go in the morning from 9 o'clock. I will reach within 20 minutes. Suppose the distance between my home to office is only 20 minutes travel time is there. So within 20 minutes, I will go there. I will park my vehicles. I will work there for 8 or whatever the working time is there. Then I will come back again 20 minutes. I will drive my vehicle, and again I will park my vehicle near to my home. So can you see the utilization time of electric vehicles? So 90% time it is unutilized. Only 10% time we are utilizing. So what you will do with your vehicles in this 90% of time? So what people are doing, people have adopted this kind of technology that is known as aggregator. So this aggregator is supposed to communicate with the grid, and it works as a mediator between EV batteries and to the grid. Suppose we have this distribution network and we are connecting one EV to the distribution network, right? So that is not the feasible solution, or I would say a very promising solution, because there will be some losses in the systems, and if you are sending only a small magnitude of power, it will lost inside the transformer or inside the line only. However, if you have bulk number of or n number of batteries or 200 batteries, suppose each battery is rated at 20 ampere, we have 200 batteries, you can think about the magnitude of current. So people are using this aggregator. They combine whole power at aggregator. Aggregator communicate all these EV batteries with the grid. I mean, through aggregator, all these EV batteries will communicate to the grid, and this aggregator will combine all the power, and then bulk amount of power can be sent to the grid, so that this battery itself, whatever the battery bank we have, it could act as a power stations. Right. So these 200 EV batteries which are located in the society, these 200 EV battery combinedly, they can act as a power plant. Instead of having these EVs and they are at rest, they can act as a power plant itself, and they can support in voltage regulation and frequency, right? Voltage and frequency regulation during when we have peak demand, when there is huge demand of reactive power. Because these charger are enabled, these are the bidirectional charger, and these charger are enabled to support to reactive power demand, as well as they can mitigate the harmonics which are there in the systems. So this bidirectional power flow, bidirectional chargers are very important, and there is a new trend in this bidirectional chargers. So unidirectional chargers, not only when we have peak load demand, we cannot integrate the charger with the grid. So this is one of the aspects. So apart from renewable integration, this is new technologies which we have, like grid to vehicles. So by combining 200 EV batteries connecting with the aggregator, and it could communicate with the grid. So this power plant, this batteries, number of batteries could act as a power plant, power stations, EV power stations, and they can support the power grid in a big way, apart from renewable integrations. So based on level of charging, it could categorized as a level 1, level 2, level 3. And then based on, we have AC connectors or DC connector. Based on the charger number of supply phases, like if you have slow charger, it could be integrated with the single phase. However, if you are talking about semi-fast charging or fast charging, then we have to use this 3-phase supply to feed the power. Otherwise, single phase maximum 16 ampere we can take. Obviously, you can parallel them, but maximum current which you will draw from a single socket, that is 16 ampere. So you cannot go for the high power station with the single phase supply. Now, so one classification we have seen depending on the various parameters. Now, if we go to the further classification, suppose we have solar-based power stations or charging stations. And now we have to classify the solar-based charging stations here. So we are going for a particular topology, right? Particular topology means where this charger is integrated with PV and grid. So here, if you have single-phase grid, we can integrate various onboard chargers. If you have 3-phase grid, we can go for the DC fast charger as well as for semi-fast charger. This single phase can be categorized as a single stage and 2 stage. So I'm talking about from the PV point of view. Suppose you have PV, This could be integrated directly at the DC bus, right, via this DC link capacitor, and we have this DC to AC stage, DC to AC stage, right? And two-stage system. So I mean, here we have connected various bidirectional converter and then EV batteries, right? So this bidirectional converter not only feed the power to this battery, it also act as a MPPT controller, right? So who will be responsible to control the maximum power which can obtain from this PV array? So this bidirectional converter will not control the current which is going to the battery, but it also act as a power converter which can control the maximum power from the PV array. In case of two-stage, instead of having only bidirectional converter, one boost converter is also connected at the PV side. So this boost converter is utilized to do the MPPT instead of having this only bidirectional converter, or we can say buck boost converter for battery charging. So apart from this charging, this boost converter can do the MPPT as it has only 1 degree of freedom. So you cannot say, sir, we are boosting the voltage. No, it is utilized only for MPPT purpose. So we are boosting only 20%. If you are going beyond 20%, there will be huge switching losses in the converter itself. So overall efficiency of the charger will be reduced. So this EV batteries, we can have the control via bidirectional converter or manual control, and then two-stage can also be categorized this way. Then this three-phase system can be, three-phase charging station could be categorized as the three-phase 3-wire, three-phase 4-wire, and then single-stage, two-stage, then single-stage, two-stage similarly, which I have described in case of single phase system. So this will be the another aspect of semi-fast charging of like if there is some unbalanced load, unbalancing, one of the phase is heavily loaded due to these EV chargers. So there will be a zero sequence currents or voltage, we can say, which will create some unbalancing, and neutral current will be there. That neutral current has to be mitigated, otherwise you have to make neutral conductor very thick. So I square R losses incurred in this three-phase 4-wire systems. So these three-phase 4-wire system, especially, they are designed if you have combined load, single phase and three-phase load. So these single phase and three-phase load create the unbalancing, and due to this unbalancing, we may have huge neutral current which is flowing in the neutral wire. So this neutral current has to be mitigated. People have taken three-phase 4-wire topology extra leg to mitigate this neutral current during charging. So this is the first topology which we have developed and we verified in the laboratory. So we have taken this PV array. Number of series parallels will decide the rating of this PV array, number of series parallel modules, and then we have DC-DC converter for MPPT. So it is a two-stage system. Remember, two-stage grid inductive charging stations. And the other side, downside, if you look into it, we have bidirectional converter. So two switches and one inductor are used to make this bidirectional converter. So this converter act as a buck and boost for charging and discharging operations, and it is connected at the DC bus. After that, we have this three-phase, three-leg voltage source converter. And here the input side we are using AC and DC, and output side we are getting AC. The operation of a simple converter which people are utilizing. And after that, we have some interphasing inductor which are utilized to mitigate the ripple in the currents. we have RC filter. This RC filter is utilized to mitigate the high frequency ripple in the voltages. And then we have some static transfer switches. So in very first slide, I discussed why these solid state switches are utilized, how the reliability of the system is improved when we are using these static transfer switches. So these static transfer switches are able to connect this charger with the grid, and whenever these parameters are not within the limit, then it can disconnect your charger with the, so that if any fault is occurring in the system, your charger should not be affected using that fault. So this STS will take care of this transition from grid connected to standalone and standalone to grid connected. So in case of grid connection mode, right, when grid is connected, your system, or we can say charger, I mean, it allows the charging station owner. Suppose I'm a charging station owner. So in that case, suppose there is very less number of EVs and the power requirement of these EVs is less than the power supplied by your PV array. So what I will do with the rest of the power, I will supply this power to the grid so that I can sell this solar energy to the grid owner and I can generate the revenue. So the payback period of that charging stations will be very less, right? If I'm selling the, obviously, if I have extra energy, I can sell this energy and I can generate some money, which will reduce the payback period of this charger. During outage of grid, this PV array generation, the charger utilize the EV to supply the household load in vehicle to home mode. So VSC based charging station we have, and so here you can see we have connected only one EV, right? One EV. So single EV can be charged, and the very important thing, when we are going to design this system, you have to think about what is the voltage which has to be there at the battery side. Suppose we have 240 volt battery and we have designed this for 240 volt, then we can connect only one EV battery and we can charge it. But one of my research scholar, he has connected various batteries. See, it is having 240 volt, 120 volt, 72 volt, 48 volt, and this way he has created multi EV spot based 3-phase charging stations, right? So if your DC bus is 700 volt, you need not to worry about what is the battery rating. So starting from 48 volt up to 400 volt, right? I can connect any EV batteries and I can charge these EV batteries, right? So he has given this type of concept. Obviously, when the voltage gain is very high, right? Input voltage, suppose 700 volt, we need some kind of isolated converters. So till this, I mean, is when the voltage difference is not too much, we can use the single, what we can say, non-isolated bidirectional converter. But when the voltage difference is significant, we have to go for dual active bridge converter. So he has utilized this dual active bridge converter while we have, I mean, so that we can provide the isolations in terms of charger, and it can be protected when a very high amount of or magnitude of current is flowing in the circuit. So this way he has proposed this concept, and you can see the outcome of his research. So he has published, I mean, various his research in various good journals like IEEE Transactions, International Journal of Energy, Research, IEEE Transaction on Aerospace and Electronic System, Journal of Energy Storage, Industrial Informatics. So here we have proposed the concept. Instead of solar, we have taken this wind and ancillary services. Obviously, we have improved the what we can say, we have taken the improved generator for wind energy also. We have not used any conventional generator. We have utilized synchronous reluctance machine. So this wind energy based charging stations or wind energy could be, already people have defined like type 1, type 2, type 3, and type 4. So starting from a squirrel cage induction motor, which can run at a single speed, and going up to DFIG, and then after that we have PMSM and these special machines, right? So SYRM has, certainly various benefits as compared to your DFIG, number one, and as compared to your PMSM also, because in SYRM, synchronous reluctance machine, either you can utilize as a motor or generator, it doesn't matter, but it has the advantage over PMSM and your conventional induction machine. So at the rotor side, in induction machines, we are using what we can say, we are using this rotor windings at the rotor side. So once you have winding, one current will flow and I2R losses will be there at the rotor side. People are designing these machines. Every designer is looking to change the rotor constructions so that the I2R losses, because ultimately your rotor current is affecting your total losses of the machine. So I2R losses are significant in that case, and these I2R losses are decreasing overall efficiency of the machine. So after that, they have designed this PMSM and BLDC, right? So PMSM, the problem of this rare earth magnet material, right? Still, people are depending on China, and we need to get this rare earth magnet material from the China. However, in case of synchronous reluctance machine, so leakage flux and all those problems are there in case of PMSM. However, in case of synchronous reluctance machines, we have used only, this machine is available in our laboratories also. Here at IIT Bhilai, we have this synchronous reluctance machine. Not only synchronous reluctance machine, PM-assisted synchronous reluctance machine. Because synchronous reluctance machine, one of the demerit is poor power factor. So the converter which we are utilizing to control this machine, it is the size of that converter will be, size of the converter will be large as compared to your PMSM or some other machine. Why? Because power factor is poor. Some of the reactive power we have to feed to the machine so that the power factor can be maintained, or machine itself, it will draw some amount of reactive power from the converter itself. So if you have some like 5 kV inverter, so we have to, for normal machine, so 6 kV or 5.5 kV inverter we have to use for this machine. If you are using PM-assisted SYRM, we are not making this rotor of permanent magnet material. We are having rotor of steel, but a small magnet material we are putting in the rotor bars, right? We have some, some slots in the rotor where we are putting a small magnet material, and due to this magnetic material, the power factor and the efficiency of the machine is improved from 80 to 94 or 90%. So this way, and the power factor from 0.7 to 0.8, the power factor is for this machine which is available, it is 0.96. So putting a small magnet material, this could give you the, very big advantage of and relief of this from poor power factor. So this machine, it doesn't have winding over the rotor, number one. And the another advantage, it doesn't have any kind of permanent magnet at the rotor side. Right, so we get rid of from both these problems. Now, if you have only this reluctance, it gives you the torque, and this reluctance torque, is dominating as compared to permanent magnet torque, and the machine start rotating, it develop the torque, and then we can drive any kind of load. So this generator, this type of generator we have utilized in this particular I12 transaction on industrial informatics paper. So it got published, and then obviously from the charging station side, we have worked on this power quality and then other aspect. So this is the overall design of this charging stations. and we got the control algorithms. So EV battery control, then we have VSC control, STS, static transfer switches, boost converter control. So as I told you, we have I mean, it is operating in grid tied mode as well as in standalone mode. So we have separate control for current control and separate control for voltage control. And this decision will be taken by static transfer switches. So static transfer switches, which we have connected in the first topology. So this static transfer switches will define either your converter is going to control in current control mode, or your controller is going to converter is going to control in voltage control. So this way, the voltage phase frequency algorithms, islanded control, we have gone through this, and this bidirectional converter control. So we have taken the sensed voltage and we have this reference voltage, whatever the reference voltage like 700 we have to maintain, so we can compare it, put in the PI controller. So we have inner loop, outer loop. Inner loop is responsible to regulate the battery current. Outer loop is responsible to regulate the DC bus voltage, and this way charging discharging of this battery is control. So this control is dedicated when you have only one battery or EV battery, right? In this topology, only one EV battery is there, so we can utilize this control, right? This control. Now, what about if we have this type of topology? If we have this multi EV spot based topology, then my question is, which entity or which particular battery will be responsible to control the DC bus voltage, right? So there will be a conflict of, control conflict. Who will decide, like I'm there, I will control this battery current, this DC bus voltage, and rest of the EVs, they will get charged from this constant, constant current. So we have proposed this control of multi-spot EV based charging, right? In which we have taken one battery bank, and that battery bank will control the DC bus voltage. However, other EVs which are connected at the DC bus via DAP converter or bidirectional converter, they will be defined or they will get charged depending on the SOC level. So here the state of charge, we have battery management system, BMS, and this BMS will provide the exact information of state of charge of each EVs. And using this communication, some programming in the MATLAB, we will define this like now we require with respect to 20% SOC, we can charge this EV battery with 20 ampere. So my reference will be 20 ampere and sensed current will follow the reference. So 20 ampere current will be drawn from the DC bus and it will be regulated using PI controller, and accordingly the switching signal will be given to the bidirectional converter. Similarly, we will send the percentage of SOC of EV2. It will be communicated in MATLAB. We will do some programming, and then after this BMS, this will tell you now we require 30 ampere current with respect to 10% SOC. The SOC is 10% only. So and the battery can take 30 ampere. So this EV reference will be set to 30 ampere, and this 30 ampere will be compared with the sensed EV2 current. IEV2 current. It will be regulated duty cycle. It will generate the duty cycle. This duty cycle will provide the switching signals for your control. So this way, when the SOC falls below 80%, the reference current decreases with a certain magnitude during discharge, and depending on the SOC level, your IEV reference will be decided. So here we have considered only 2 EVs, but you can consider n number of EVs, right? N number of EVs you can connect. You define the current depending on the SOC level, and these will be charged and discharged accordingly. So we have these synchronization and desynchronization controller for grid connection disconnections. And here we have sensed the grid voltage, load voltages, and depending on these parameters like IEEE 1547, if they are within the range, then we will get 1. If they are not within the range, then these STS will be off. And then we have developed some PLL algorithm also, and experimentally they have been, compared with the conventional PLL. This is the flow chart, basic flow chart, which could give you the power management among the various EVs. So this is a few results which I have put, like simulated performance under certain outage of utility grid when this grid appears. So how this battery are charged, EV batteries are charged, and then we have certain simulation performance under dynamic conditions, right? Here we have limited this total harmonic distortion, which we are discussing, starting of this lecture. And then experimental results. So it has been verified experimentally, this type of system we have developed. So here you can find out the various EV batteries with different voltages, right? We have we have utilized these 4 EV batteries, and we have various converter over here. We have PV simulator, and one controller is there, DSpace controller, and this had been integrated with these converters and EV batteries. Then, so output, you can see it is operating at MPPT, and the various results which we have obtained under various conditions. So total harmonic distortion are also maintained when the converter is switched on. So earlier it was having 11.31 and 22. However, after that, this is reduced to less than 5%. Right, under various operating conditions we have gone through. So second configurations where we have used a different operation, different modes of operations where grid to vehicle, vehicle to grid, and this has been verified, and here DAP converter we have utilized. So DAP converter control as well as biaxial converter control we have utilized. And here you can see various EV batteries we have used, starting from VB1, IB1, VB2, IB2, VB3, IB3, VB4, IB4, then VB3, IB5. 5 EVs we have considered and we charge simultaneously with the different voltage. They are not, at the same voltage. We have different voltages for EV batteries, and this way EV batteries are charged. So various simulation result, and then charging and discharging with this particular simulation, and it has been verified in the OpenRT platform also. So we have various VB1, VB2, IB1, IB3. These results are obtained by a research scholar in various platform in hardware as well as in the OpenRT platform, and then various total harmonic distortion which we got 4.1% over here. However, the total harmonic distortion we got 21.8%. So finally, conclusion of my talk. If we have charging stations which has been presented here. Which could deal with in various modes. It can resynchronize, it can synchronize, it can operate it in islanding, it can feed the power to the household load, to the grid, and it can operate under grid outage conditions. It can address the power quality issues, right? Same converter which is utilized for charging, voltage source converter. It can also address the power quality issues, right? Power quality problem, harmonic mitigation, reactive power demand. It can fulfill the reactive power demand also. Voltage less than 5%. TSD we have limited less than 5%. Not only voltage, grid current TSD and grid voltage TSD both are limited within 5%. The control has shown very good dynamic operations, multi-spot different voltage levels have been proven, and the good charging capability. So I mean, this could be the customer choice to select charger according to the requirement of EV. I mean, different voltage conditions. We need multi-spot based charging stations, on board, off board, various stations. So thank you very much. This is my, I think, last slide of references. I would like to thank first the organizer who have invited me, and the secondly, I mean, the participants who have listened me patiently, I mean, 1.5 hours. Now I would take the questions, I mean, from the audience, I mean, participants. If you have any question, you can unmute yourself, you can ask. So that is from my side.
Thank you, sir, for your remarkable lecture. Your ability to simplify complex idea and inspire critical thinking is truly commendable. We deeply appreciate your valuable contribution. Now I request to participant, please ask a question, and you can also write in chat box.
And moreover, if anyone is interested to do research in this area, they are welcome. They can contact me. They can send a mail. If I mean, they are interested in PhDs, I mean, those who are master, I don't know, I mean, what kind of audience are there. So if you are interested in any research positions, I mean, right now I have a couple of research positions opening. So if anyone is interested, anyone who want to join, I mean, I also have one PhD position. So anyone if interested, they can contact me. They can write me over mail. So can optimizing algorithms in control system of charger improves power quality? So actually here we are not using optimization technique. Optimization technique people are using in various aspects. Here we are using some kind of adaptive filters, right, to improve the power qualities. Right, optimization algorithm you can utilize. Suppose we have to find out the PV this PI parameters. So people are utilizing these. I mean, for this application, power converter applications. So this PI parameter can be optimized using some optimization algorithm. But as far as the power quality is concerned, people are using various adaptive filters. They can I mean, tune the various step sizes of these algorithms if you go in deep of these algorithms. So these step sizes are tuned, and we can extract the fundamental component from your polluted load currents. Right, so basically adaptive filters are used for this purpose, power quality purpose, not optimization algorithm. Optimization algorithms people are using for tuning of PI controller, and then MPPT purpose also people are using this various algorithms so that the quickly we can search this maximum point, right? Because in MPPT you could find out we have two conditions. One is steady state and another is dynamic conditions. So dynamic conditions means how fast you are going to track the maximum point starting from, suppose we have, if you see the IV characteristic, initially the point will settle at a zero current because we are not obtaining it. As soon as you will switch on your PV array, this point will, if you have put the algorithms, your point will try to track this PV point. So it is starting from your x-axis and it will try to go up to the maximum value. So this is known as your dynamic condition, and once it reaches to the maximum point, your optimization algorithm must be very fast so that it could track within a millisecond or so. And the another aspect, it must not oscillate. It should not go left and right. It should stick at a maximum point, right? Maximum point where we are getting the maximum power. So in this way, this optimization algorithm people are utilizing, because conventional INC and Peterman observer algorithm, they have some disadvantages, right? Steady state response is poor, and other, what we can say, the dynamic response of tracking of these algorithms are poor. So these optimization algorithms can be utilized. Here people are utilizing adaptive filter to control this current, this voltage source converter for power quality purpose.
Sir, how will decide the grid parameter, and how will decide the range of grid parameter for microgrid systems, sir?
So already, I mean, they are defined. Like if you are talking about this IEEE 1547, suppose you have solar inverter and you want to connect this solar inverter with the grid. So once you will measure the grid parameters, suppose for single phase, we have 230 volt 50 hertz. So if you want to synchronize your solar inverter with the grid, you have to generate the voltage of 230 volt magnitude and 50 hertz frequency. Then only your, so see, suppose I'm bringing a black box. I would say I'm bringing one black box and I'm putting two wires to my single phase socket. It doesn't mean it will start injecting power to the grid. So we have to use some controllers which could synchronize the output of your solar inverter with the grid. So synchronization part is very important, and your parameters must be within the range of your grid parameters, the parameters which you are generating from the this solar inverter. Right, so they have already defined, like if we are operating within this range, then you are able to synchronize, otherwise you will not be able to synchronize. So simply whatever the grid parameter that we have to put into our control, and this control must act in this way so that it can be synchronized with the grid. So grid parameters are already defined. Accordingly, we have to control our converter.
Thank you, sir.
Thank you, Selen sir. Maybe there is no query because chat box is empty from all the query.
Yes. Thank you, sir. Thank you for the opportunity to discuss these few things on which I'm working. On these things.
It is so informative.
Thank you, sir. Thank you so much.
Okay, sir.
Okay, sir. So, yeah. Can I leave?
Hello.
If you permit.
Is also
okay.
Yeah. Sir.
Hello. Dr. Salen ji, myself, Professor VK Giri, head of department. So I was.
Namaskar, sir. Namaskar.
Namaskar. I was throughout connected to the lecture. It was very informative, and the students, we would like to see you offline mode also. So you belong to UP or?
Yes, sir. UP. I belongs to UP nearby Kanpur. Actually, I visited this Triple MUT couple of times. I was in NIT Surat, then along with Dr. Sabaraj Arya and Maurya sir, I visited this place.
In which year?
I think in 2019, if I'm not wrong, December 2019. Okay. I visited, and there was one FDP, so I delivered one lecture over there.
Okay.
And earlier in UPCon, I visited Triple MUT. I presented a paper. At Triple MUT.
By the way, I was not there at that time. I was on deputation. So
okay, sir.
I came back in 2020. So we would like to have you once more. So very soon we will invite you.
It is
in
an
some other.
honor and privilege to, I mean, visit this place. I mean, this is very secret
No,
place as.
Your
Yeah.
talks will be very, or interaction with our PhD students
Yeah.
will be very fruitful. So we will like to very soon. We
Sure,
will
sir. Sure, sir.
also.
Yeah.
Nice.
Thank you, sir. Thank you so much.
Okay,
So,
sir.
yeah, Nadeep, sir. So, can I leave? If you.
Yes, sir. Yes.
Yeah, thank you.
Yes,
Thank
sir.
you. I will take leave. Thank you so much. Thank you, all of you. Thank you for joining and, I mean, listening this session.
Thank you. Nikita.
Please pay attention